Hello and welcome to topic 2 of week 1 for Geology of the National Parks. I'm going to get right into this one. So to recap the chemistry we talked about in the first topic lecture, we use the amount of silicon dioxide, also called just silica, to classify earth materials, also called rocks, as felsic, intermediate, mafic, or ultramafic. Now it's important to realize this only applies to igneous rocks, that is, rocks that originated from some kind of molten material, lava or magma. And in that context, we use silicon dioxide or silica or quartz to classify rocks as felsic, intermediate, mafic, or ultramafic. Elements that like or prefer to bond with silicon are sodium and potassium, and elements that like or prefer to bond with iron are calcium and magnesium. Aluminum is fairly common in all of these rock compositions. So in geology, we don't really work with pure elements very often, but instead we work with substances made up of combinations of elements, which are minerals. Rocks, on the other hand, are collections of mineral grains or natural glass, which basically is obsidian, natural glass made by volcanic processes. Minerals are unique chemical formulas with unique crystal structures, different arrangements of the atoms that make up the crystal structures of any mineral. A mineral is something like quartz or feldspar or mica, and these are components in rocks like granite or sandstone or gneiss. These are all rocks, and they are all made up of mineral grains. So what is a mineral? Let's define that. It has to be naturally occurring, so a natural diamond is a mineral, but a lab-grown or a synthetic diamond is not a mineral. It has to be solid at room temperature, so liquid mercury, even though that is, in rare cases, naturally occurring, that is not a mineral. It has to be inorganic, so no carbon-hydrogen bonds. It lies outside of what we call organic chemistry. Now, there are minerals that contain carbon. That's what organic means, it's carbon-based, but there are not minerals that contain carbon-hydrogen bonds. So coal is a rock and not a mineral. It also has to have a fixed chemical formula made from elements. That means that a mineral has one composition. Now, there are spectrums of compositions within mineral families, but those are all defined by specific ratios of different elements to each other. And a mineral has to have an orderly crystalline structure. So, for example, the mineral calcite likes to form in these sort of three-dimensional parallelograms, or the mineral pyrite prefers to make big cubes. These are examples of a crystalline structure. Here on this slide we have feldspar, where you can see its crystal structure also, well, it makes these weird shapes in this particular example. And then over here we have quartz, which is silicon dioxide, silica, as we've already discussed. And it likes to make hexagonal towers when it's in a condition that prefers the growth of large crystals like this. Feldspar is what we call an aluminosilicate. Silica is the basis of all or most crustal rocks and rocks in the Earth's mantle. But a lot of them contain aluminum and indeed potassium, so this is a felsic mineral. It contains aluminum, potassium, and silica, Si3O8. These are considered felsic minerals because they are based on silica. So now we're going to talk about the phases of items. In this case, we're going to start with talking about ice. What phase it's in, that is phase of matter, solid, liquid, gas, or the other one, supercritical, depends on two factors, its temperature and its pressure. So here in this chart we have a phase diagram for water, a simplified version of it. You have liquid water occupies most of the territory around pressures and temperatures we tend to exist at, so most of the water we see is liquid. However, you can do two things to liquid water. You can cool it down and get solid water, or ice, and you can heat it up, at which point it will boil and create water vapor, or steam. The lines follow the trend at which water becomes either a liquid, a solid, or a gas. These are called phase boundaries. And they intersect at a couple of points. One of these is called the triple point, where you can get your water to exist at a solid, a liquid, and a gas all at the same time. According to this chart, that happens at 0.6 kilopascals of pressure and at 0.01 degrees Celsius. This is not a pressure regime that we get normally on planet Earth at the surface, so you have to lower the pressure using a vacuum pump to get to this kind of pressure. Down below, we have a more detailed phase diagram for water. At atmospheric temperature and pressure, which is right here, 1 atm, 1 atmosphere, and 0 degrees Celsius, which is a temperature we see regularly here in the Pacific Northwest during winter time, we have water likes to exist at either a solid or a liquid. If you increase the pressure quite a lot, all the way up to 1 billion pascals, 1 gigapascal, your solid water will melt and turn back to a liquid at freezing at 0 degrees Celsius. But then if you increase the pressure even more, it goes back into solid, but it's in a different phase. This one is called ice 6. And if you keep increasing the pressure, you can get into more ice phases, ice 7, ice 10, ice 11. These are just different crystal structures, different arrangements of water molecules inside that ice. As you increase the pressure or the temperature, your ice atoms will rearrange themselves and form a different crystal structure. There's one thing in these phase diagrams which is important to note, especially in water. It's called the critical point. You can see it easily up here. That is the point where the line between liquid, and gas becomes blurred. You just end up with a fluid. It's called a supercritical fluid. When you get down to the pressures inside the Earth, water isn't really a regular liquid anymore. It's a supercritical fluid, which allows it to move very easily through the mineral crystal structures of different minerals present in the interior of the Earth. That's called the critical point, which happens at a certain temperature and at a certain pressure, above which you don't have liquid or gas, you just have supercritical fluid. To recap our geothermal gradient, the Earth is hottest at the center, inside the core, and it's coolest at the top of a crust, where you have 0 or near 0 degrees Celsius temperatures. Inside the Earth in the core, you're approaching 7,000 degrees Celsius, very, very hot. So the inside of the Earth is extremely warm, and the surface of the Earth is extremely cool by comparison. And that line that traces between, here it uses radius, or depth to the interior as a proxy for pressure and temperature. That line of temperature and pressure as you go into the interior of the Earth is called the geotherm, or the geothermal gradient. Here's how phase diagrams relate to the interior of the Earth. Let's start from the inside, the deepest part of the Earth, the inner core. It's solid, as we've already discussed, because the geothermal gradient, shown here in this chart as this heavy black line, crosses the phase boundary, which makes the innermost iron core solid. It's not a lot hotter in the inner core than it is in the outer core. The sort of inner-outer core boundary is about the same temperature as the inside of the inner core, so that's why the geotherm plunges sort of straight down here. But the phase boundary line between pure solid and beginning to melt is crossed by the geothermal gradient at that inner core, outer core boundary. And the outer core is all liquid because the geothermal gradient, the temperature and pressure, dictates that the mostly iron and nickel outer core is molten at that location, at those pressures and temperatures. The base of the mantle, or mesosphere, is where that phase boundary gets crossed again by the geotherm, and we have the mantle being solid. It's a plastic solid because it's still pretty close to that solid line, but it is still a solid. You could punch it and break your hand. It is a solid rock. However, the higher up you go, things get a little bit more complicated, and we'll talk about that in the next slide. But the difference between the solid inner core and the liquid outer core is actually what gives us our magnetic field. The solid inner core is rotating relative to the liquid outer core, and because it's all iron and nickel, which are ferrous or magnetic metals, elements, that means we get a magnetic field generated. This is called the geodynamo, and that is the mechanism by which we get our magnetic field. So what about the mantle? The mantle is a little bit more complex, well, with regards to this course anyway, than the inner and outer cores. And the pressures and temperatures inside the Earth, the geotherm, are generally nowhere close to melting for the lithosphere. That's this upper portion of the chart. And we get actually quite close to melting about 150 kilometers down inside the Earth, where we have the asthenosphere. And that is a material property boundary where we go from solid rock in the lithosphere, more or less solid rock in the mesosphere. But then the asthenosphere is a very plastic solid. It's like silly putty, because the geotherm is sort of flirting with the solid to liquid line. This is called the solidus. And because we have a very low degree of partial melt, there's very little liquid, but it's just hot enough that those minerals easily deform, easily slide past each other, and we have plastic deformation inside the lithosphere. So it's very close to melting, but it's not molten. The lithosphere is floating on that almost molten solid rock that is the asthenosphere. Then the mesosphere remains close to the solidus, the thermal phase boundary here, but it never gets quite as close until you get to the outer core mantle boundary. Some other ways to think about brittle versus elastic versus plastic. We talked about this in the last lecture, but just to review, butter is an example of a solid you can have either as plastic or as brittle. If you put butter in the freezer, you can grate it on a cheese grater. You do this a lot in baking. The previous instructor who made this lecture was a baker, and so she included butter as a great example in her lectures. You can break frozen butter with a knife. You can also grate it on a cheese grater. But if you let that butter warm up for a little bit to come to room temperature, you can indent it with your finger. So that's the difference between your lithosphere is frozen butter, and then your asthenosphere is room temperature butter. And it deforms plastically, not elastically, but plastically. You cannot put it back into its original shape. Well, I guess you could if you put it back in your stick of butter mold, but that's beside the point. It is permanently deformed. So to recap, here are our layers of the Earth. By chemical composition, we have a crust, mantle, and core. And by physical or mechanical properties, we have inner core, outer core, mesosphere, asthenosphere, and lithosphere. Remember, these are different. The crust incorporates both oceanic and continental crust. The lithosphere incorporates both kinds of crust as well as the uppermost mantle, and the asthenosphere incorporates also parts of the uppermost mantle. The mesosphere occupies the bulk of the Earth's volume, which is the lower, roughly 2/3 of the mantle. And so now I'm going to introduce the concept of isostasy. The lithosphere is more or less floating on the asthenosphere. Both layers are solid, but the lithosphere, the upper one, is solid and brittle and doesn't flow, while the asthenosphere is plastic and does flow. A lot of diagrams you will see come across, both in textbooks and in even the scientific literature, you will see people will say crust and mantle when they mean lithosphere and asthenosphere. That's just colloquial. It's easy to mix those up, but they are different. Remember that. Isostasy is basically the principle of buoyancy between the lithosphere and the asthenosphere, the relationship of thickness of the lithosphere and how the asthenosphere responds to that. So in this simple cartoon on the right, let's start with a uniform block of lithosphere of less dense crust, and floating above an asthenosphere of more dense mantle material. That would be asthenosphere. If we excavate a big crater inside the lithosphere and make a big pile, kind of like a mountain, also on the lithosphere, the asthenosphere will flow in response, and it will cause the crater to float up buoyantly and the mountain to sink down until they reach a point of what's called isostatic equilibrium. The asthenosphere fills in the void below the crater and moves out of the way, flows out of the way below the new mountain. On the left here, this diagram shows it a little bit differently, a little bit more realistically, where say you have two continents crashing together, that creates a big mountain range where your lithosphere is thickened. And then over time you have erosion removing the mountain range, and the asthenosphere below it will flow in and cause that to buoy back upward in isostatic uplift. On the Earth, we also get this during ice ages. During the last ice age, for example, most of North America was covered in a miles-thick ice sheet. That's a lot of weight that is put on the crust, on the lithosphere and the asthenosphere, and the asthenosphere actually flows out from under it. The lithosphere flexes. It can flex slightly, even though it is brittle. It flexes and sinks downward. Then once the ice sheet removes, we have isostatic uplift, bringing the crust back up to its current level. In Antarctica, it's got 1, 2, in some places 3 miles of ice, and the actual rock surface for a lot of Antarctica is below sea level. If you snapped your fingers and took all that ice away, Antarctica would begin to rise upward until it reaches a point of equilibrium with the asthenosphere. Now we're going to move into heat transfer, which is a consequence of the geothermal gradient. It's really hot in the inner core, so heat wants to flow to an area where you have low heat. Two substances of different temperatures are in contact, the interior of the Earth and the exterior of the Earth. Heat must flow from the heat must flow from high temperature to low temperature. Heat will flow until the interior and exterior are at the same temperature, which is called thermal equilibrium. So how is heat transferred within the Earth? There are 3 mechanisms for heat transfer. There are radiation, conduction, and convection. Radiation works just like a radioactive material. It radiates out. If you have a lump of uranium sitting on your counter, you are being bombarded with radioactive rays that are coming off of or radiating out from your lump of uranium. Heat does exactly the same thing. If you put a rock in your oven and take it out and put it on your counter, it is going to radiate heat until it reaches thermal equilibrium with the surrounding atmosphere. However, rocks are pretty bad at radiating heat. Even though the interior of the Earth is nearly 7,000 degrees Celsius, or Kelvin rather, the exterior of the Earth in some places is well below freezing. We have permafrost, we have ice sheets. So radiation is not very important in the cooling of the Earth's interior. Second, rocks are pretty poor conductors, so conduction just isn't really that important of heat transfer in the Earth. So that leaves us with convection, which is the main mechanism by which the interior of the Earth transfers heat to the exterior and the planet cools. The planet Earth cools mainly by convection of hot, that means plastic solid, stuff, rising and sinking down. A great way to visualize these 3 methods is from a campfire with a pot of water. The campfire radiates heat up to the water. Then the handle of your pot gets hot from conduction. The heat of the campfire heats up the pot, and because the handle's attached to the pot, the handle gets warm. That's conduction. And then finally, the water inside your pot is convecting. The water is heated at the base of your pot. Hot water rises and cools off and sinks back down toward the edges of the pot. That's convection. And exactly the same process happens inside the Earth. So how does a planet convect? Well, there's a lot of different models. We're not entirely sure what the dominant mechanism of convection is. Is it individual convection cells inside the lower mantle and the upper mantle? Are these behaving separately? Versus, is it mantle plumes, also called hot spots, bringing up material from the core boundary directly up to the lithosphere, the bottom of the crust? What is the main mechanism for convection? Are we convecting the whole mantle, or are we convecting parts of the mantle? We don't really know, and that's very much an area of active geophysical research. I'm going to put on this quick video for convection currents, just to show you what they look like in water. This is just water that is being heated and cooling off. Wait till this really gets going here. So we have the red water rising. There is a hot cup of water beneath this part of this glass or acrylic tank, this clear tank, and the red stained water is being heated by that hot cup, and it is rising as a result of that. The blue water, which is unheated, is being dragged up by it. But as we sit here, as we watch it get sped up, that hot material rises and spreads out at the top of the convection cell, and then as it cools off on the edges of the tank, it sinks back down, where it is reheated. We can see some of the blue and some of the red reaching, let me go back a little bit, reaching that hot area once again and re-rising toward the top. This video is linked on D2O. I recommend you watch it if you need more help understanding convection currents. So to recap, the asthenosphere and mesosphere are both plastic solids, so they convect. But the lithosphere is a brittle solid, so it doesn't convect, it instead breaks. So what happens if the asthenosphere is convecting underneath the lithosphere? Well, we get large broken chunks of lithosphere, and we call these tectonic plates, which introduces the concept of plate tectonics. The basic idea, to summarize, the interior of the Earth is cooling by convection cells. The brittle lithosphere is broken up into pieces called tectonic plates. The continental lithosphere, that is the part we sit on, the land part, called the continental plate. The continental lithosphere is too buoyant to sink into the mantle because it's made of those rocks, those minerals, those felsic rocks and minerals that are less dense, and so they don't sink down into the mantle. The oceanic lithosphere, however, which is made up of mafic minerals and rocks, is very heavy and dense and cold, so it subducts, it sinks down into the hot uppermost asthenosphere and mantle. These tectonic plates meet each other at things called plate boundaries, and there are three kinds: divergent, convergent, and transform. A divergent boundary is a place where two plates move away from each other because the plastic mantle is rising at this location. This is where we get new oceanic crust. Check out this video, which shows how this works. We get hot mantle material migrating upward, which can force apart continental plate, either oceanic or continental. And as that happens, they start to spread apart. And new crust is being formed at that divergent boundary. And in the ocean, we call this a mid-ocean ridge. And this creates sort of a conveyor belt spreading away from the center. When you have hot mantle material reaching the base of the continent, you get a rift basin, and eventually this is how ocean basins are created. For example, in this series of images, we have the hot mantle material rising and bending upward the continental crust, where you get volcanoes stretching and warping and thinning of the continental crust. Over time, that crust starts to spread apart and thin, creating a rift valley or rift basin. And eventually, over time, the continent completely splits and you have the creation of new oceanic crust, a new mid-ocean ridge, a new spreading center in between the two continents. So then we have ancient ocean at the edges of this new ocean basin, and then young new ocean right in the center. And this spreads apart. We have this right now in the Atlantic Ocean. The mid-Atlantic ridge is the center of the Atlantic Ocean, and it is pushing open the Atlantic Ocean. In these rift zones, the primary rocks that are being erupted from the volcanoes at the mid-ocean ridge are called basalt. Basalt is a chemical composition of rock. It is a mafic volcanic rock, basalt. This sort of continental plate splitting apart is happening right now in East Africa, the East African Rift System, where we have a series of rift basins incorporating the African Great Lakes, Lake Malawi, Lake Tanganyika, not Lake Victoria. It's made from different forces, but a whole bunch of different lakes are forming in the rift basins along the new plate boundary that is forming here in East Africa. But we'll talk about this more next week. Convergent plate boundaries. We just talked about where two tectonic plates are splitting apart. Now we're going to talk about what happens when they come together. A convergent plate boundary is a place where two plates move towards each other because the lithosphere is sinking at this location. Oceanic lithosphere is destroyed by the process of subduction, and subduction is our second new featured word for this week, so make sure you write that down and give it a good definition. Subduction always involves volcanism, which produces intermediate compositional volcanoes, which are scenic and explosive. Mount Rainier is a volcano formed at a convergent plate boundary, where we have the oceanic lithosphere sinking down underneath our North American continental crust. The lithosphere and oceanic crust begins to partly melt in the subsurface as it sinks down, and that feeds volcanoes and forms what's called a volcanic arc, parallel to that plate boundary. The actual plate boundary is represented by an oceanic trench. In our case, we have a very shallow trench where the Juan de Fuca plate subducts beneath the North American plate, and that trench is paralleled by the Cascades volcanic arc, of which Mount Rainier is a part. Continental crust is too buoyant to subduct, so instead, when two continental plates collide, you get a big mountain range, like the Himalayas. The Himalayas are occurring where India is colliding with the Eurasian tectonic plate and creating the world's tallest mountain range in the process. Then finally, the third type is a transform boundary, where two plates are sliding past one another. This is a consequence of other plate motions, such as segments connecting mid-ocean ridges. If two segments of a mid-ocean ridge are spreading at different rates for some reason, then you're going to have a transform boundary between them. There's another famous transform boundary, the San Andreas Fault, which accommodates the lateral sliding motion between the Pacific plate, which is moving in this direction, and the North American plate, which relatively is moving in this direction. Relative, not purely from GPS vectors or anything. But the difference in motion between the two plates creates a sliding boundary, a transform boundary that we call the San Andreas Fault. And transform boundaries can be very complex, very complicated. As this course goes on, we will learn more about them. An important part of plate tectonics is the opening and closing of oceans, which is what we call a Wilson cycle. In this example, we start with a continent rifting apart by that mechanism we already described, and unto the point where a spreading center forms between the two continents. And then as rifting continues, we have the opening of a new ocean basin. However, over time, this basin becomes older, and as it becomes older, the lithosphere at the ocean's edges becomes cool, and eventually it becomes so cold that it will break off of the continent and start to subduct, sink down into the mantle. And that is how we get new subduction zones forming. And eventually, these two continents start to becoming closer to each other. They're moving closer to one another, and this is going to be the assembly of a major megacontinent like Pangaea. The cycle of spread apart continents like we have right now and supercontinents like Pangaea is part of what we call the Wilson cycles. And now we have the continents forming a mountain belt. To recap, most of these volcanoes and most of the world's earthquakes are occurring at plate boundaries. We can see here around the Pacific Rim, the Ring of Fire, it's called, even though these are independent systems that do not affect one another, is where the world's dominant areas of volcanism and earthquakes seismicity are. And here we can see a map of the world's earthquakes colored by depth. We have shallow earthquakes at transform boundaries like the San Andreas and at divergent boundaries like the Mid-Atlantic Ridge here. And then we have deeper earthquakes along subduction zones where cold lithosphere is sinking deep into the mantle. So we have deeper earthquakes at subduction zones and shallow earthquakes at divergent and transform boundaries. Another interesting part about convergent plate boundaries is the concept of accreted or exotic terrains. For example, most of the western portion of North America is composed of what we call exotic or accreted terrains. So for a long time, the western margin of North America was a large, big single subduction zone. About 20 million years ago, half of that subduction zone went away and became the San Andreas Fault. But before then, islands on the forerunner to the Pacific Plate were occasionally getting stuck, smeared off onto the North American plate as it subducted over time. So think about an island arc like the Hawaiian Islands or the Philippines or Indonesia sitting on a tectonic plate, let's say the Pacific Plate, and then over time, those string of islands will get glued on to North America as the Pacific Plate subducts and scrapes those new terrains on to North America. A good way to envision this is by a grocery store conveyor belt where we have an oceanic plate delivering sets of islands over time to the North American plate. And then eventually these will all get bunched up against the end of the conveyor belt, which is what we have as the North American plate. And that is called exotic or accreted terrains. This will be a recurring theme throughout the course, particularly up in Alaska and throughout the western United States. So to recap, the Earth cools both by convection currents, or cells, and mantle plumes. Mantle plumes give us large eruptions of basaltic lava, such as the flood basalts. The Columbia River basalt is a good example of these, or the Deccan traps in India, if you've heard of those. Large outpourings of basalt over a big area is called a flood basalt. That's one of the things that happens when you get a mantle plume reaching the lithosphere. The other thing that happens is a hotspot volcanic system, where you have a stationary plume of very hot material feeding a chain of volcanoes that slowly moves away as the tectonic plate moves, leaving a chain of volcanoes, such as Hawaii. Now, the Hawaiian Islands are just the youngest portion of a very long chain of underwater mountains that stretches all the way up to the Aleutian subduction zone here in Alaska and Russia. The Emperor Seamount chain we can see is this linear portion up here, and then there's this bend where the motion of the Pacific Plate changed, and the Hawaiian Islands have been forming ever since then. These mantle plumes appear to be stationary over long periods of time, allowing us to track the tectonic plate motions. So let's start from the youngest, the island of Hawaii. It is still actively currently forming. At the time I record this, there was an eruption on Kilauea 3 days ago. So we are still forming the island of Hawaii. It is 0 million years old. Maui, the island of Maui is about 1.3 to 0.8 million years old, so 800,000. That's just when it breached the surface. There are active volcanoes on Maui. The active volcano of Haleakala still produces lava flows every 1,000 years or so. But the farther northwest you go, the older the islands get. Oahu, 2.6 to 3.7 million. Kauai, 5 million years old. And then you get into the seamounts, the islands that are so old they have actually sunken down and are no longer standing above the surface. Midway Atoll, 27 million years old. Ogine Seamount, 55 million years old. And the farther away you go, the older and older these islands get. And they have left behind a trail of volcanoes as the Pacific Plate has moved over the stationary mantle plume feeding the Hawaiian Island volcanoes. And that's all for this lecture. I will see you next week.